Now as we get into the D block, things get a little bit more complicated. In the first shell, the only orbital that I had was the s orbital. In the second shell, I had a 2s orbital, and I picked up a 2p orbital. In the third shell, I'm going to have a 3s, a 3p, and also a 3d. And so right here in my transition metal block of the periodic table, this is my D block on the periodic table. So for all of the elements that fall within that transition metal region of the periodic table, I know that their highest energy electrons are going to be placed into a d orbital. But when we write our quantum numbers for the d orbitals, the first shell where we see a set of d orbitals is the third shell. So right here in group 4, this corresponds to where we will be placing electrons into my 3d subshell. For yttrium, atomic number 39, I'll be placing electrons into my 4d subshell. For lanthanum, 5d, actinium, 6d. So that for my elements in the d block, that shell where that d orbital resides is always going to be equal to the period number -1. So that as I move across that d block, I'll be placing my first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10 electron systematically into those d orbitals. So that if I look at the fourth period on the periodic table, I can write an electron configuration for a calcium atom. I know that for calcium I need to place 20 electrons into orbitals. So as I write my electron configurations, I'm going to start at atomic number 1. The position of hydrogen and helium on the periodic table tell me that the first 2 electrons for calcium are going to go into the 1s orbital. So my electron configuration starts with 1s2. Electrons 3 and 4 for lithium and beryllium are going to be placed into the 2s orbital, 2s2. Electrons 5 through 10 are then going to be placed into the 2p orbital, so 2p6. That gives me a total of 10 electrons so far. As I move across the third period, electrons 11 and 12 are going to be placed into the 3s orbital. So I have 3s2. Electrons 13 to 18 are going to be placed then in the 3p orbitals, 3p6. That gives me a total of 18 electrons that I've placed once I get to argon on the periodic table. Electrons number 19 and 20 are then placed into my 4s orbital, 4s2. Based on calcium's position on the periodic table, I know that its electron configuration ends in 4s2. I know that I need to have placed 20 electrons into the lowest energy orbital configuration. So that as I move to scandium, atomic number 21, I'm going to start at hydrogen and work my way to scandium by placing the electrons in the orbitals that I encounter as I move from atomic number 1 to atomic number 21 on the periodic table. Hydrogen and helium tell me that those first 2 electrons go into the 1s orbital. Lithium and beryllium tell me that electrons 3 and 4 are going to go into the 2s orbital. Boron through neon tell me that electrons 5 through 10 are going to go into the 2p orbital, so that gives me 1s2, 2s2, 2p6 for the first 10 electrons. Sodium and magnesium tell me that electrons 11 and 12 are going to go into my 3s orbital. Electrons 13 to 18 are going to go into my 3p, so that's going to be 3p6. So at this point I have 1s2, 2s2, 2p6, 3s2, 3p6. That places my first 18 electrons. Potassium and calcium on the periodic table tell me that electrons 19 and 20 are going to go into my 4s orbital, so I have 4s2. And electron number 21 is going to be placed into my 3d orbital, so 3d1. That takes care of the placement of the first 21 electrons for scandium. Any element that comes after scandium will have an identical electron configuration for its first 21 electrons as we see for the 21 electrons that we have in the scandium atom, such that all of our electron configurations will build upon each element that comes before it in the periodic table. So that if I were to move all the way across that D block, I would have 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10 for zinc, And when I got to gallium, I would be placing 31 electrons into the orbitals. So that means that for electrons 1 and 2, I'm going to place them into the 1s orbital, just like I did for hydrogen and helium. Lithium and beryllium are going to give me 2s2 for my next 2 electrons. I'm going to have 2p6 taking care of electrons 5 through 10. 11 and 12 are going to go into the 3s orbital. 13 to 18 are going to go into my 3p, so that's going to give me 3p6. 19 and 20 are going to go into my 4s, that gives me 4s2. 21 to 30 are going to go into my 3d orbitals, so that gives me 3d10. And electron number 31 is going to go into my 4p orbital for gallium. Based on its position on the periodic table, I already knew that its highest energy electron would be placed in a 4p orbital, and that its electron configuration would end in 4p1. I want you to pause the video and write the electron configurations for strontium, zirconium, and indium. So that if we write the electron configurations for strontium, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. We know that as we write the electron configuration for strontium here, atomic number 38, it's in the s block, it's in the 5th period, and it's the second element in the s block, so we know that its electron configuration ends in 5s2. That means that its highest energy electron is placed in that 5s orbital. For zirconium, based on its position on the periodic table, it's in the d block, it's in the 5th period, it's the second element of the d block. Based on that, we know that its highest energy electron is going to be placed into a 4d orbital, and its electron configuration is going to end in 4d2. So that as we place all of those electrons, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. Finally, for indium, as we look at indium's electron configuration, it's in the 5th period, it's in the p block, and it's the first element of the p block. So we know that for indium, its highest energy electron is placed in a 5p orbital, and that its electron configuration ends in 5p1. Now, as we start getting into some of these longer electron configurations, we're going to see value in understanding how we would write what's called the noble gas core abbreviated form for our electron configurations. And in order to do that, what we're going to do is we're going to find our element on the periodic table. So here for strontium, we're in the 5th period. We're going to be looking for the noble gas in the period that precedes it. So that means that the noble gas at the end of the 4th period is krypton. So that for strontium, if I write krypton in brackets, that is abbreviating the first 36 electrons, placing them in orbitals in a manner that is identical to that with which we would do for krypton. So together, that's going to take care of my first 36 electrons, and that's going to be my electrons in the 1s orbital all the way till the electrons in that 4p orbital. So the only electrons then that I have to place for strontium that come after those 36 electrons for krypton are electrons 37 and 38. And so that's going to give me an electron configuration in the noble gas core abbreviated form of krypton followed by 5s2. I can add up the total number of electrons by knowing that krypton placed 36 electrons due to its atomic number, and then I placed 2 more electrons into my 5s orbitals for electrons 37 and 38. For zirconium, zirconium is also in the 5th period, so that means that we can use krypton to abbreviate the first 36 electrons. So that means we can abbreviate electrons in the 1s all the way through the 4p. But we have to write all of the electrons that come after electron 36. So for zirconium, that's going to mean electrons 37, 38, 39, and 40. So we're going to have krypton in brackets, followed by 5s2, 4d2. We know that we placed 36 electrons from krypton, 2 electrons then into the 5s, 2 electrons into the 4d, and that gives me a total of 40 electrons, which is what I need for zirconium. Finally, for indium, atomic number 49. Krypton will still be my noble gas that I use for its noble gas core abbreviated form to abbreviate the electrons in the 1s through the 4p. I have to take care of the placement of the electrons after 36 up to 49. So I'm going to have krypton in brackets, followed by 5s2 for electrons 37 and 38. Electrons 39 to 48 are going to be placed into the 4d, and then electron number 49 gets placed into the 5p. So I have krypton followed by 5s2, 4d10, 5p1.